Hi, Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Okay, so since that today is a public holiday, so I'm recording this slide or this lecture for you guys, for those who classes. I hope that you can download it or watch the video in the YouTube once I upload it. So at least you still can what we call that proceed with the lecture and still able to what we call that kind of like attend the online class. Okay, for your group, I know that we already covered a bit of bending moment or ultimate bending moment and the ULS ultimate limit state in our previous lecture, which is I think we stopped in the middle of the slide or something. But since that I'm recording this slide, so I decided to record it, the explanation from the beginning of the slide till the end. Okay, so there will be like non-stop, and then this video will be what we call solely uh, for ultimate bending strength lecture. Okay, all right. So here, as we can, you guys can also uh, scan the QR code, okay, just to record your participation, okay, in terms of probably when you watch the video, it's like you are attending or spending time with to the course, so you can download the QR code. Sorry, you can scan the QR code. Okay, so let us start. Main outcome of this lecture is students must be able to determine the bending capacity of the pre-stressed concrete beam. Okay, so bending capacity of a pre-stressed concrete beam, is quite because once we know that for pre-stressed beam, we design it based on serviceability limit state, which at this point, okay, we have all the parameters that we need for a pre-stressed concrete beam where we have designed it using principles that we applied in previous lecture. Okay, so with all the parameters, for example, what are the parameters? The parameters will be, for example, like the pre-stress force, okay, the eccentricity, which is determine the location of the tendon that we want to put. I want to place our tendon in our pre-stress beam. Okay, and we also have designed the sufficient size or section of our beam, okay, based on based on our location, based on our what we call um, section moduli and so on. Okay, so we have come up with the consideration of what is our moment in terms of service and also at transfer and all. So we have we come up with one section that we can use for our beam. Okay, and at this point as well, with manual diagram, tendon profile, and all, we also determine our stress force and our eccentricity. Okay, so since that we have all the parameters, basically we have uh, the beam or the pre-stress beam, with the all sections, and process force and all. So we want to know if our section is it is it is it can is it is it capable in terms of carry our ultimate limit state condition, which is first will be of course our bending, and then second will be our shear. Okay, so because we know that these two are the main failure that will happen, will experience by our beam, okay, at ultimate limit state. Okay, so yeah, we didn't design based on ultimate limit state, but we have to make sure that, okay, our beam, okay, our pre-stressed beam can sufficiently work, or can sufficiently what we call that carry or carry the scatter the bending moment capacity of at ultimate limit state condition. Okay, all right. So here, it says that generally, we know, as I explained before, we design our pre-stress beam based on solidity limit state. Okay, however, we all have to ensure that the design has sufficient moment and shear capacity at ultimate limit state. Okay? So you have to ensure that. So we consider all partial factor of safety on loads, okay, for loads and material. It's kind of like not much different from reinforced concrete design. You have gone through this. We have designed using all these parameters before, okay. But the only difference that you probably will notice is in RC, in reinforced concrete design, we didn't consider any pre-stress force, okay. But with this design, okay, in pre-stress beam design, okay, to check the bending moment capacity, we will consider our pre-stress force, okay. So the pre-stress force must be multiplied, okay. The pre-stress force must also be multiplied with what we call as partial factor of safety, which stated as gamma m equal to 0.9. Okay, so this is as what stated in UK National Annex, favorable effect. Okay. All right. So ultimate limit in general, okay, just want to point this out. Okay, we have two main what we call resistance that we have to check. One is the ultimate moment, and second will be the ultimate shear. Okay, for shear we have two conditions, which is we say it has to be determined under crack condition and also crack condition. Okay. So loads are factored as in accordance to EN 1990 section 6. Okay, so design variables and permanent load are stated as what you did for your reinforced concrete design. Okay, there's no different about that. So you still have coefficient of partial factor of safety for imposed load, for what you call for dead load, okay, and also you have additional of what we call from the pre-stress force, okay. So partial factor of safety for loads, okay, which is gamma f at ultimate limit state. So you have the GK, you have the QK, right, and you have the WK. So pre-stress P. So I think this is a very common table that you see, okay, you used before. Okay, the table uses simplified combination permitted in EC2. Alright, so where you have like a gamma F. Okay, gamma F can be for imposed load and also what you call dead load. Okay. So for the material properties, okay, that was the general for the loading or for the actions, or we call it action in Eurocode. Okay. So here for the tendon, right? For tendon, we have one thing about tendon is you get this table normally from manufacturer. Okay, it's not provided in Eurocodes. Okay, because normally tendon it depends on who is our supplier, where do you get our tendon from. Okay, then the manufacturer or the supplier will provide you all these parameters for their tendon, that we use. Okay, for example, like this table taken. Okay, so we have like the strand type, the tendon type. So you have three type. Basically, this is kind of like okay. So this is like a general. So this table, if you want it to be perfect, as I said, you get from from the manufacturer. But this table is based on data from the S5896. Okay, in general. But this one, as I said, this is kind of like what you call as a guideline only. Okay. But you could get more detailed data from the manufacturer that providing your tendon. Okay, that's wrong. Okay. All right, so you have standard, super, or drawn, okay, with the acronym here. So the diameter, which is in mm, which is the sizes available. Okay, so that's why I said if you have from your own manufacturer, you know, every manufacturer will have different specs, you know, specification of their product, of their tendon. So they have their own, you know, diameter and all the sizes, and also the FPT, which is the strength of the tendon, okay, the ultimate strength of the tendon, and this one the FP01 0.1K, which is the strength, the stress of the proof stress, okay, normally slightly lower than the ultimate strength, and this is the pre-stress force, okay, the initial pre-stress force, and this is the maximum pre-stress force, okay, that you can use, all right. Okay, then you have table concrete. Okay, this table, I think this is very common table you can get, you can see, all right. You can take this from table 3.1, okay, table 3.1 in your Eurocode. Okay, so each will have you would see that, you know, for different classes. Sorry. So for different classes, you know, you different strength and also different modulus elasticity of the concrete. All right, so analysis of section. Okay, as you can see, pre-stressing steel begins to behave as conventional reinforcement when loads on pre-stressed member increase above the working values and cracking occurs, right? So when you have like what you call, even though you provide you know, tendon, not the regular tendon as you provide for reinforced, you know, you are not using a force bar, but then still the behavior is still the same, okay, because you know, you place it the way how you place the tendon, right, and you will you it will behave when you let, of course it will behave it as it will behave like, you know, regular reinforcement bar, right, and it will increase under above the working values, and also of course it will cause cracking. Okay, that one very common. You will see that, right? So the behavior of pre-stressed member at ultimate inner state is exactly as the conventional reinforced concrete member. Okay, so accept that the initial strain in the steel must be considered. Okay, so we even though we have like, you know, the tendons being pre-stressed and so on, but the behavior of the beam is still the same, right? The behavior is still the same, which we have to consider. We have to consider the initial strain, right? Before of the steel. And lastly, we have like reinforcement bar can be used if tendons are insufficient. Okay, reinforcement bar can be used if tendons are insufficient, provide shear and bending moment. Okay, so in a way where you have like what you call that, um, um, if say you provide your tendon inside your pre-stress beam, okay, but then of course you don't design your tendon, okay, to cater for your shear and also your bending, but somehow or other by providing your tendon, sometimes it is enough and it is sufficient enough to cater for your shear and bending moment as well. Okay, but it's not always gonna be the case. Okay, it means that there are situations whereby the tendon itself is sufficient to cater shear and bending moment, but there is a condition whereby your tendon is not is insufficient. Okay, means it's not sufficient. Right, means it cannot cater. It's not sufficient to cater shear and bending moment. So how to know? Alright, how to know? Right, how to know what we call our tendon is sufficient uh, on for shear and bending moment is we have to check, we have to calculate, and then we have to check the sufficiency of our tendon. If say that our tendon is not sufficient, then we have to provide additional reinforcement bar. Okay, we provide additional reinforcement bar Of course, we provide bar to cater for the moment, and of course, we provide shear to get link to cater for shear. Okay, so in terms of calculating tension forces in each layer of steel, okay, we could have like few layers, all right? It's not only like our tendon, it's not going to be like only one layer. It could be like two layers, all right? It will be like probably three layers, okay? It depends on what we want, what we have designed for our beam, okay? So in general, we would say total steel strain. Okay, total steel strain is due to bending, and also initial strain in the tendon. So we consider that the total is not only going to cater for bending, but we have to also include the condition of initial strain. What is initial strain? Initial strain is whereby when you apply your pre-stress force, okay, to your tendon. So it is also included. Okay, it is also included in your total strain. Okay, so total tension capacity is compared to the compressive force developed by uniform stress of 0.567 FCK. Right? So this value is still similar with what you have used for your microscopic design. Okay, so but in the condition of you have two capacity, one is the tension and one is compressive. So in this case, normally if you have tension, you cater for, in your RC is catered by reinforcement, but in this case, our tension is catered by what we call by our tendon. Okay, and by using the concept of equilibrium, okay, when you equal the condition of your compressive and also your tension, so we can get what will be your ultimate moment resistance, okay, at that for that particular section. Okay, and what you see here next to the what we call the figure here. So here is a very common what we call tendon. So the ultimate tendon, where you have the pull stress, okay, divided by the gamma m, which is 0.9, with the E given here is 205 kN per mm square. Okay, so how to analyze, right? So how to analyze our pre-stress beam? So we analyze our pre-stress beam in terms of knowing which part is the compressive, which part is the what we call that tension. Okay, in terms of calculating what will be the ultimate moment resistance is by using rectangular stress block. Okay, I think this is quite hopefully it doesn't sound alien to you. Okay, everyone should at this point should be familiar with rectangular stress block, considering that you have gone through this in your microscopic design. So I hope that by me going through this, it's only going to be like what we call refreshment. Okay, I mean refreshment means like, it's something that for you to recall, you can recall it back. If say you forgot about it, at least when you hear me explaining about stress block, you can still recall what is actually stress block. Okay, so you have like gamma is equal to 0.8. Okay, and your gamma, because it depends on your, sorry, not gamma, so it's a lambda. So it depends on your concrete strength. So your lambda is equal to 0.8 if say that your concrete strength is lesser or equal to 50 MPa. Okay, but if say that your concrete strength is bigger than 50 MPa, but somehow rather lesser than 90 MPa, so you have to use this equation in terms of to compute your lambda value. Okay, one question, what is actually lambda value? So if you look here in terms of your stress block, okay, this is your lambda value, all right? So lambda value is actually your height, the height of your stress block. Okay, stress block whereby you will see the area that will be what we call that will be for concrete or for compression zone. Okay, because if we determine our neutralization, our neutralization height, okay, sorry. Yeah. So here in general, you will know that your X will be somewhere here. Okay, your X will be somewhere here. Okay, so but then since that to consider a few conditions of your concrete stress block, so we have like sufficient. We have kind of like multiply it with coefficient which is will be shorter about 20%. So that's why we have like 0.8. Okay, so it will be slightly shorter than the actual X. So how to know how much it's shorter? In terms of the height, where we have to multiply with lambda. Okay, that is lambda, which is this is the height of your stress block. Okay, so for your mu, right, it's also based on the condition of your concrete strength. So based on if say that your concrete strength is lesser or equal to 50 MPa or is bigger than 50 MPa. So in general, what is your mu is used for is to multiply with uh, your concrete strength. Okay, your concrete strength, which is calculated by 0.567 FCK. Okay, so in this case, if say that the concrete strength is lesser than 50, then your mu is 1.0. So it will remain 0.567 FCK. Okay, that's what we call this is for stress. Okay, and this is for strain. Okay, and as for strain, you have two conditions as well. Anything above the neutral axis we consider as compression zone. Anything below the neutral axis we consider it as tension zone. Okay, so in this case, the compression zone, okay, is whereby we identify it the maximum of the strain. Okay, for concrete will be strain Cu3. Okay, and for steel, which is a tension, is equal to strain S. Okay, because we can see that this is the position of your, say this is the position of your tendon, and the tendon cater for your tension condition of your beam. And when you make a straight line here like this, you can draw it slightly at the center of your tendon. Okay, so if say that you have another layer of your tendon, so say that something like this, okay, then you will have another strain S1 and also strain S2. Okay, so it means that you have two values of your strain. Okay, so here you will see that the force, the stress, the force for your compression, okay, which is in this direction, and also the tension in the other direction. So it must be like always opposite direction of your compression state and also tension state. Okay, so distribution of strains and stresses across the section in bending. Okay, so RC bending theory, so assume that concrete will crack in the regions of tensile strain. So after cracks occur, all tendons are carried by the reinforcement. Okay, so that's a way of how it will behave. So plane section is assumed remain plane, means that there will be no like different angle and so on. So after straining, so that linear distribution of strain across the section can be considered. Even though in a real behavior of a beam, it will not behave like that, because once you press something, of course it will like moving around. But somehow in terms of for simplicity, to simplify our calculation for our design, we assume it remain static, remain plane, right? Don't have any skewed or angle and so on. Okay, so if you look here, so our section say that we have two layers of reinforcement, which is your tendon and reinforcement. This is very common, okay, where you have like reinforcement at compression and also reinforcement at tension. So anything with dash here is actually represent your reinforcement, your condition at compression side section, and you have a S which is at tension. So this is actually experienced, okay, by the beam. right? With this reinforcement. So you have like a strain Cu, which is the ultimate concrete strain. Okay, we consider, but here you have what we call strain for steel at compression. So steel compression. Okay, C is meant for compression, and we have also considered that the strain ST, which is the strain of steel at tension. Okay. And generally, this is how our triangular stress block will look like, okay, for stress, okay, with the X and so on. But somehow or other, to make an accurate, what we call definition of stress block for reinforced concrete, to represent the what we call the compressive part, is we consider it parabolic, because that is how concrete behave. Okay, but since that it's not easy to calculate or to consider parabolic in terms of stress block calculation, that's why we come up with rectangular. So, but somehow change between the parabolic to rectangular will have some kind of some what you call that differences. So then our height of our stress block must be reduced. So that's why we consider the lambda value, which is taken as, depends on the strength of your concrete. In this case, taken as 0.8. Okay, by considering that the concrete that we consider in this case is lesser than 50 MPa. Okay, so this is like the definition of the stress block, why we come up with our rectangular one. So here is where we consider that the stresses are very nearly proportional to the strain. Okay, so occurs under working condition. So use as, this is what we use. Okay, use as SLS. Okay, represent the distribution at failure when the compressive strains are within the plastic range. Associate with design for the ULS. Okay, so this is actually we decided to use, but to simplify the rectangular parabolic, then we simplify it to become rectangular, okay, for our stress. So somehow or other, this is the simplified stress block for concrete section, okay, and then you can see all the notation are written. This is your FCC, okay, for your compressive. This is for your tension, your X, and also your H. Okay, so we also always say that it's like, this one is H minus X. Okay, so let's take a look stress strain relationship for materials that we use for pre-stress beam. Okay, at this point, generally you have like it's not something new or something different from RC design. It's still the same, especially when you're talking about concrete and steel. Okay, because these two materials also used in concrete design. Okay, in reinforced concrete design. Okay, but we're just gonna go through, okay, one by one. All right. So concrete behavior is presented by a parabolic stress strain relationship, as we mentioned before, up to a strain of strain C2. Alright, so what is strain C2? Is this 0.002. This is the strain C2. Okay. Sorry, Cu2. This is C2 and then this is Cu2. What's the difference between these two? This is not ultimate, this is ultimate. Okay. So here is whereby you have like given alpha multiplied with FCK divided by the parameter material for concrete, which is 1.5. Okay, and then we have 0.85. When you divide 0.85 with 1.5 is whereby you get 0.567. Okay, factor 0.85 allow for difference between the bending strength and the concrete cylinder crushing type, because it's not exactly the same. We get the FCK is from the concrete cylinder crush, testing. When you get, you compress, and then you know what will be your concrete strength or cube test. But somehow rather, when applied to a beam, so the exact strength that you determine from the test, from the compressive test, is not exactly the same as what the beam experience or the beam had. So that's why we are considering only 85% of the strength. So for the gamma C, which is equal to 1.5 partial factor of safety for concrete, and for the ultimate strain, we are taking 0.0035 according to the figure. Okay, because we consider which is typical for concrete that is lower than C50. Okay, right. So I hope you all guys are clear, because see, look, this is the parabolic curve. Okay, it's not linear to the strain, so it's a parabolic curve relationship to the strain. Okay, curve of the stress. Okay, so here where you have next will be reinforcing steel bar. So the behavior of steel is analytical in tension and compression. Actually, it's the same. Okay, either the location of it is at the compression or is at the tension. So it behaves linear in elastic. You will see it's linear, like a straight line. Range up to the designed yield stress, which is Fyk divided by the gamma s. This is the point. So this is the ultimate normally, okay, whereby the steel passes through the linear state. And the elastic range stress is equal to elastic modulus multiplied with the strain. So we have like that one is very common, where you have stress is equal to modulus multiplied with strain. And you see that your E can be taken as 200 kilonewton per meter square, and you can calculate your yield strain, okay, by taking your stress, your ultimate stress divided by your E. Okay, so in general, you will have your strain is around 0.00217, depend by taking your strength of your steel bar equal to 500 Newton per mm square. The relationship between the neutral axis and the maximum concrete strain, which is strain C2, and the steel strains are given by strain. So determine the stresses in reinforcement can be evaluated from stress strain curve. Okay, so if you look here, your strain ST, tension, is equal to strain CU, D of minus X, and also for at compression, your steel is equal to strain Cu2 X minus D dash over X. So let's see how we get to that relationship. So if say that you have like your beam, okay, as shown before, means that you have two layers of beam, two layers of steel. One is one layer, first layer is at tension, and the second layer is at compression. So say that this is your neutral axis. Sorry. Okay, so here you have your rectangular section. Okay, then your and your strain. Let's say that you have like your strain, something like this. Okay, so little bit what's wrong with this thing? I'm not sure why. You just discard first, try it again. Okay, alright. So let's draw that back. Okay. Right. And this is a this one here. And this is kind of like a strain down there, distribution. Okay, and oh, sorry. Okay, so it should be like something like this. Okay, and here is actually written as your ultimate concrete strain. Okay, which is will be the not concrete, means compressive in a way, right? Concrete. Okay, and then you have two layers of your layers of your reinforcement. Means that you have two layers of strain coming from the steel. So you have strain steel at compression and you will have strain still at tension. Okay, so you have two conditions. So one parameter that we know, we obviously are aware, is one is the distance or the height of the bottom reinforcement, which is normally we say it is equal to D, and we also know the location of our reinforcement at compression, which is normally we denoted it as D dash. Okay. So here, when you have, and then also another parameter that we know, this is your x. Okay. So when we want to consider the calculation of strain ST, so the issue is we don't know what is the strain ST. Okay, we don't know what is the strain contributed by steel at tension and what is the strain of the steel contributed at compression. Okay, so what we can do is we can equal the triangle that we have for our strain, which is if you do like a ratio, so you have this relationship SU2 divide by your x. Okay, this one divide by your x. Okay, you have your strain SU2 divided by your x. So it's also equal to your strain ST divided by its height. Okay, this triangle, the big triangle and also the small triangle. So you can have it proportion because it is still from the same diagram. Okay, so you can write your height here. This one is actually equal to D minus V. Okay, and when you calculate your it will be over D minus X. So your strain ST is equal to strain CU2 divided X multiplied with D minus X. So that's how you get the value. Okay, if you look the other way around for your strain SC, which is at compression, okay, you will do the same thing with consideration of your strain SC, okay, is equal to your x minus with D dash, which is equal to strain CU2 divided by x. So when you calculate, you will get strain ST is equal to strain CU2 divided by x multiplied with x D dash. Okay, so I hope you guys are familiar with this. Okay, nothing new. We have gone through this in your RC for your stress plot. Okay, that's how you get the value. Okay, so determine the strain, stresses, and reinforcement can be evaluated from the stress strain curve. Okay, so we know the strains and the depth of your material axis. At ultimate limit state, we can say that the maximum compressive strain in concrete is equal to strain CU2. Okay, so this is kind of like what you might get in terms of calculating your x. Okay, and your strain C2 can be taken as 0.0035. Okay, and you have like your concrete class with the if this is only valid for concrete class that's lesser than 50 MPa. If it's more, then you have to refer directly from the table. Okay, so for the ultimate limit, okay, for FYK equal to 500 Newton per nm square, so you will have your strain ST equal to strain Y, which is equal to 500. Okay, divided by 1.15 multiplied by 200 times 10 power of 3, which is 0.00217. Okay, so the ultimate strain here, okay, whereby you have your strain C2 is equal to 0.0025, is typical for concrete which is lesser than C50 over C60. Okay, what else I want to say? Okay, so if you put the value of the ultimate strain, okay, strain values at tension and also your concrete, then actually you can estimate your x will be 0.617. Okay, this is just when you have this statement, okay, it means that your steel have reached its tension. Okay, means has yield. Okay, because you use 0.00217 by considering the ultimate FYK of 500. Means it cannot go beyond 500. So what will be your ultimate strain value for your steel at tension will be 0.00217. So that's why when you use this, you kind of like say that your X is equal to 0.617D when your reinforcement is yielding at tension, okay, for ultimate inlet state. But however, member inflection should be ductile, and that failure should occur with gradual yielding of the tension steel, not by sudden compression failure of the concrete. What does it mean? It means that even though you considering your ultimate strength of your steel, which is 500 MPa, by saying that the maximum strain will be 0.00217, but somehow or other, when the steel fail, it will not suddenly will go up and fail. Okay, so they will be like, it will take time, the gradual yielding, because we know how steel behave. Okay, so in terms of when you allow, when the yielding process, okay, it kind of like enable of the formation of plastic hinge, which if you look into properly, it will, kind of like where you have the redistribution of the maximum moment. Okay, so it will resulting more safer and economical structure. So it means that it will not shoot up straightly to 0.617. So here is whereby you will, once you get your what we call that, your Fs, okay, and your Fc, and of course you know what will be your X at the point where X is equal to a value where the condition of your compression force will be equal to the tension force, and you calculate your moment by taking your Fs. What is Z? Here you see the point Z. Z is actually taken from the center of your what we call compression force to the tension force. From the compression to the tension force. So lever arm, we call it Z is equal to your lever arm. Okay, so because we want to multiply the moment. So multiply the moment, so you have this in this direction and your compression in this direction. Okay, one in this side and then one on this side. So you have it calculated. So this is must be total, because you might have not only one layer of your steel, that you could have like multiple layer of your steel. Okay, and you have this value as well, and then this one is multiplied with your lever arm. Okay, lever arm can be calculated by considering your D minus with 0.45x. Okay, why is 0.45x is where you you consider the value of half of your area. Okay, but in this case, why 0.45 is actually you take the lambda is equal to 0.9, not 0.8. So here you have like here 0.45. Okay, x. Okay. Lambda is a value. Previously, if you look into the because one thing to highlight, because my notes we are referring to the some of the values change. I mean. Because it depends on the addition that you refer. Okay, so in this case, you're referring what you call that, the addition. There are slightly some kind of error here that we notice when we deliver the course, when I go through the examples. Okay, so the lambda in this case is actually taken as 0.9. Okay, and so when you 0.9 divided by 2, because the distance is divided by 2, so then we will have it become the distance here it becomes 0.45x. So you want to know the distance of your Z is by taking, this is your D, okay, the height of your to the center of your reinforcement. Okay, you minus with the 0.45x, okay, which is the half of 0.9. Okay, and this is where you have this point, and you put then you calculate your ultimate moment at your tension and also your compression. Okay, so at your compression is very straightforward, whereby you have 0.567 FCKB, okay, multiplied with 0.8x multiplied with also the z will be your the distance to calculate your moment. Okay, all right. Okay, now, so we will go through your example, okay, the calculation of ultimate resistance moment. So please take note, I have distribute this assessment for you to redo back this example. It's very important for you to, try yourself, redo this example so that you will get the experience and you'll be able to understand better in terms of the topic and in terms of how to calculate it. Okay, right, let's take a look, let's go through it together. Okay, calculation of ultimate resistance moment. Okay, so we have one section of pre-stress beam, okay, pre-tension beam, which is provided with 10 5 mm wires with characteristic strength, which is the proof stress of 1,600 Newton per mm square. So if this wire initially stressed to 1120, so what does it mean? So it means that the pre-stress force is 1,120 MPa, and the losses, which is the K, is 30%. Okay, so estimate the ultimate moment resistance of the section. If class C 35 means the concrete strength that we use is 35 MPa is used. So figure below shows the concrete, the cross section of beam and the stress strain curve bar for the wire. Okay, so let's take a look one by one, shall we? So we have one beam. This is the beam cross section. So given is the width is equal to 120. So the height given as 300. Okay, so what you will see here, we provide, at this point, we have provide, means that we have designed your pre-stress beam. Okay, we designed the pre-stress beam by providing 10 5 mm. So you provide 10 5 mm tendon, and then it depends on you how you want to, put it in your beam. But in this case, they put it in 2 layers, which is 5 below and 5 upper. So by putting the, 2 layers of your tendon, so you will have 2 strain, contributed from your tendon. So you will have your strain, which is we say as, so same color with the other. So let's change it a bit. Okay. So you have your strain here, which is we denoted it as strain S below. Okay, bottom. Okay, and the upper part here, one more layer, which is we say strain, strain still upper. I don't know why A, or maybe A is like a first layer or second layer. B is the second layer. Okay, there's no like upper and bottom. Okay, it doesn't matter what notation you are using as long as you understand the first layer and second layer. All right, then you have the ultimate strain that we consider, okay, for concrete, because it's above the neutral axis. Say that the neutral axis somewhere here. Okay, above neutral axis with the x is equal to this point. Okay, and we take it above as a compression side, and the maximum of the concrete strain is equal to 0.0035. Okay, and here we have what we call that the stress block. This is the strain. Okay, so we have identified what will be the possible strain. Okay, we know the tension contributed by the 2 layers of your steel, your tendon, and the concrete contributed by the concrete itself, which is 0.0035. Okay, so here is the stress. Okay, so for the stress, what you can conclude is where you have also still have 2 conditions, which is the compressive and also the tension. So as we say about stress block contributed by the concrete, and we simplify it become rectangular. So whereby we have it 0.8x here, okay, and we have the ultimate what you call that of your width, which is maximum what you call maximum stress of your concrete, which is 0.567 FCK, and this is your force of your concrete, okay, which is what because normally force will act at the center, right? So you have the force, and you have also the what you call that the force for your steel. Okay, if you look here, it will act like a center by considering the two layers of your tendon. Okay, the center, you know, you don't have, you know, like one each, like FSA, FSB, something like that. So the total it will be FS. Okay, total of your force of for your steel. Okay, and the figure below shows cross section beam and then stress strain curve for the wire. So this is the properties of the wire, the material properties, okay, of the wire. So we say that the ultimate strength is 1390. Okay, when you say the ultimate means that is already you know, you are considering how to get it is by 1600, which is the, you know, characteristic of your proof stress, divide by your partial factor of safety will give you 1390, which is will be the ultimate strength of your steel, of your tendon, that will be used to calculate your moment. Okay, and this is your E, and when you drag down you will get your strain, which is how you get the strain is actually is a simple calculation where you have you know, stress is equal to E multiplied with strain, and then you have like you know the stress, which is 1390, okay, and then you divide it with your E, then you will get your strain. Okay, yeah, here we go, right? So all the properties are here. So let's take a look the calculation. So here is whereby you calculate first your area of your, because you need to know what will be the area of 5 mm wire. Okay, for each, yeah, we're talking for each, okay, wire, the area of it, because you have 10, so you might be multiply with 10 later, or 5, okay. So stress in steel after losses, we consider the initial pre-stress force, which is given 1120. Okay, you multiply with the K, which is the 30%, which is 0.7, and also the what we call the gamma P, which is 0.9. So you multiply it, you will get 705 Newton per m square. And you have strain in steel after losses. Okay, so you will consider, so once you know what is your Fs, you know what is your force, you divide with the E for your tendon, you will get what will be your strain after losses, because you are considering your force, you know, of your stress after losses, okay, which is less than the yield strain. So if you look into the yield strain of your strain Y by considering 1390 as your ultimate strength for your tendon, okay, and then which is you will find out is will be lesser, okay, which is still means okay, because it has to be lesser. If it's more, then it means that you still cannot capture your moment on your strain. Okay, so the depth X must be found for which the compressive force in the concrete is balanced by the tensile force in the steel. So these two values must be balanced, must be equal. So you have compressive force and also tensile force. Okay, and this will contribute to your ultimate moment when you multiply it with your lever arm. Okay, so Z is your lever arm. So you will take these values, and you, as a first attempt, you try X is equal to 150 mm. So why first attempt 150 mm? So at this point, actually, you don't really know where is the location of your X. Okay, as we know that you are given the section, which is the height is 300. Okay, so if you look into general, so you will see that it will be half, like 150 like that. So then your okay, so they will be at the center. Okay, but this is your x, so this is your x value that you want to determine. So in general, your x can vary. Okay, your x can vary either if equal to 150, which is exactly at the neutral axis, or it could be like slightly upper, as we say here, is like 130, 120, 100, and odd. Okay, so your what you call your triangle will vary. So it's either here 130, you could have a slightly lower, then you have it like maybe 100. Okay, so it will differ from from x value to another x value. Okay, so because at the point you want to get your stress block for this, which is somewhere here. Okay, because your consider is slightly above the neutral axis, and this is your FC, and this is your FS. So these two must be equal. Whenever because once you get your value of your when you consider your x value, the value of your FC also will be changed. So you must get at a point where your FC is equal to FS. Okay, so final steel strain. Okay, at this point, like we say, the total steel strain must include the value of pre-stress strain, which is this value of pre-stress strain plus with bending strain. Bending strain is the common strain. Okay, so steel strain at top layer, which is you have the gamma S. Okay, so not gamma, I mean the strain dash SA. So you will have like 0.034. Where do we get the 0.0034? It's coming from the tendon pre-stress, pre-stress strain, okay, plus with bending strain, which is we are considering Allah Akbar. 175 minus x divided by x, okay, multiply with strain CC. Okay, so this is the value. So because you have like strain SF A divided by 175 minus x is equal to your strain CC divided by x. Okay, then you put it up, then you will get the strain CC multiplied with 175 divided minus x divided by x. Okay, so you have A, right? And when you calculate the value by considering the x height, so you will get 0.046 for your upper strain, the first layer of your steel strain. Okay, and you will do the same for your bottom layer of your steel strain. Okay, by taking, because now if you look into the changes will be, this one is 275. Okay, and this one will be 175. So what is this value? This is your D value. This is your D value. Okay, why D value? Because you have like okay, so the position of your tendon. Okay, so the position of the tendon here, at this point this is 100, this is 25. Okay, so it must be like somewhere in the center. So this one, if you calculate the position of your D, okay, so means like D, say DE, alright, so 100 divide, sorry, how is it? So you have 125 on here. So you have to multiply 300 minus 125. Okay, so if you calculate, okay, 300 minus 125. Okay, so you will get your DA is equal to 175. Okay, so the same thing if you have like this part. Okay, so means that your 300 divided by 25, okay, which is give you 375, which is your D. Okay, all right. But the most important thing, you need to know the location of your 24th and 100th distance of your wire from bottom or from top. Okay, and so once you have different D, of course, you're going to get different strain for each value, which is this also you get 0.0073. Okay, so if you look here, this one is 0.0046 and this one is 0.0073. This is, you will see it's slightly greater than 0.0678. So what is 0.0678? Okay, this is the value. So it means that the ultimate strain that can be held by the tendon is equal to 0.000678. So whenever, so you have to ensure that when you calculate your strain, A will not be more than 0.0678 because if not, it's beyond the capacity of your tendon. Okay, but in this case, for your bottom part, you get it more. Okay, so later we will see what will happen if you get more because you have to consider a few things. Okay, so from the stress strain curve, the corresponding steel stresses are, you have the top layer and bottom. So you just multiply. For example, like your top layer, you have your strain and that you have calculated, okay, and you multiply with the modulus, you immediately will get what be the stress at the top. Okay, and the same thing for a little bit different from your bottom layer because since that your strain is greater than the maximum capacity of your tendon strain, whereby 0.00678, so that's why you will consider this stress 1390 Newton per meter square. So what is 1390? 1390 means the maximum stress that can be captured by the tendon. Okay, right? Because this is the maximum, because this is the ultimate value of your that we want to consider for your tendon in our design. But since that this is greater, so then we just use the maximum. Okay, so forces in steel and concrete. Okay, forces in steel and concrete. So how you get, all right? So basically, for steel, we know that we have two layers. So when you have the two layers, you have to calculate the summation of each contribution of the layer. Okay, so you will have your stress, two values of your stress, which is 943 and 1390. Okay, that will be your stress. Then you multiply with the area. This is the area, okay, of your tendon, and then you multiply with the number at that particular layer. Okay, particular each layer lah. For this case, for bottom layer and the top layer is 5. So 5. So that's why you add and then you multiply with 5 for each of the stress. Okay, and then you will get the total will be equal to 212 kilonewton. Okay, that will be the total tensile force. Okay, how about the total compressive force? So total compressive force is very straightforward because you just, this is your force. Because you know that this is your force. And you know the limit of your what you call your stress FCD, sorry FPD, FCD is equal to 0.567 SEK. Okay, so this is your B. Okay, and this is your 0.8x. Okay, so you multiply all these values. Right, 0.567 multiplied with 0.8 multiplied with the B, and you will get your force is equal to 248 times 10 power of 3 Newton. Okay, so check force FC in concrete is larger than the force S in steel. So therefore, a smaller depth of neutral axis must be applied. Okay, so here is where you will see that is it the same or not? Your force that you calculated for your steel and the force that you calculated for your concrete. Okay, obviously you will not see it is the same. So what you do? Okay, what you do? So you have to try again with smaller depth of neutral axis. Okay, because just now we try x is equal to 130. So maybe this is mm. So when you calculate this by considering x is equal to 130, you calculate, you get at the end your force for steel is 212 and the force for your concrete is 248. Okay, so what you have to do, you have to repeat back the same calculation but using different value of your x. Probably your x now you take as a 110 mm probably, or 100 mm probably. Okay, so you have to try one by one. Yeah, I know it's tedious. All right, but you have to come at a point whereby when you calculate your forces here, the value of steel force and also the concrete force will be the same. So when you get it the same, then you can conclude your x optimum for your section is equal to 133. Okay, so in general you have to try and error. So that's why normally to calculate this, we don't really calculate manually. Alright, so normally we either calculate it using Excel, or you calculate it using a software, or you calculate it using MATLAB. Because you have the iteration, you have to have a loop. I think you learn about looping in your numerical before this. So to write a coding and maths coding, okay, to iterate the value until the iteration process will stop until this value is the same. So then you can get what will be your x. Okay, but normally how I say, if you are using if you are answering test question or exam question, normally I will limit it into 3 calculation. Okay, after 3 then you can conclude, just proceed. Okay, because who has the time to calculate manually one by one, right? It will be very lengthy. Okay, and take so much time. So the depth of neutral axis, okay, as we know, is concluded as 1 to 123 mm. Okay, so therefore, okay, once we know that the x is 123, then we can calculate the moment. So how we calculate the moment is by taking the value of your fs, okay, but there are two sides that you can consider, because we know that the x we determine, the optimal one determined by considering your fs is equal to your fc, means that your force at tension side is equal to force at concrete side. So it's equal, it's the same value. So it doesn't matter if you calculate your moment using the tension side formulation, or you calculate your ultimate moment using concrete side, concrete side. Okay, you will get more or less the same value of your ultimate moment because your forces are the same value. Okay, so say that we take the tension side first. So once you take the tension side, actually you have to consider your Fs multiply with Z, since that we have 2 layers of your Fs, okay, of your stress for your steel. So you will calculate it. If you look here, they put it outside the bracket, the two parameter that's similar, which is the common parameter, which is the numbers of the tendon and also the area of the tendon, because we are using the same tendon for both layer, and then the number of the tendon also the same. Okay, and then we put it outside the bracket, and then we focus on calculating the what you call that, the Fs, which is the force. Okay, the force for the first layer. Okay, and the D for the first layer, for the upper layer, the FA, and multiply with 0.4 times 1, 2, 3. So you look here, 0.4 here is taken by 0.4 is because you take 0.8 divided by 2. Okay, then we get 0.4. So if you look here, before this, you if you see 0.45 means that it is 0.9. Okay, so I'm not, there are kind of like inconsistency in this slide. I'm really apologize about that. I will try to improve it better next time, because I didn't realize that some the examples taken is from different edition than the one that I showed before. Okay. Sometimes things happen, right? You didn't notice, but the most important thing, you understand where the value coming from. Okay, and you have here you have 175 minus 0.4 times 123. Okay, so this is very nearly because your x is equal to 123, and you take your force for the second layer, for the bottom layer, which is 1390. Okay, and you have your D also for your second layer, and you multiply with your your 0.4x. Okay, this is actually considered as your Z. So this is actually considered as your Z, because you want to know what's the value of your moment by multiply your force multiply with the lever arm. So you will get like 43.1 kilometer meter. Okay. Okay. Alright. So this is 43. Say that if you don't want to consider each layer. Okay, you can use average D as equal to 225 mm. Okay, so you will get more or less like 41.2, something like that. Okay, if you don't want to use like don't want to calculate each layer. Okay, right, so your D can be, then you can get like the average value of your your stress. So your MU will be taken like 254 kilonewton multiplied with okay. All right, so that one's the tension side. So let's take a look on the compression side. So when you have compression side, it's actually much more straightforward, because you only have one value. So you have 0.567 FCK here. Then you have the B. Okay, you want to multiply with the area. Okay, multiply, and then you have this as your 0.8x. Okay, and then of course you have this force, C, then you want to, this is your Z, so you want to multiply with Z to get your moment. Okay, so you put the values of your B and your, this is your X, this is your X, your B. Okay, you multiply, and then you get, this is your Z, the position of your force, this is your 0.4x. Okay, this is your the D minus, and you will get it around 441.2 kilometer meter. Okay, so you look here, it kind of like more or less the same. Okay, all right, the same values. Okay, and that will be your ultimate moment. Okay, so you design your, that will be your ultimate moment to consider based on your section. Okay, right. Then you check, of course, you check either your what you call your ultimate moment, is it sufficient against your moment resistance. Okay, ultimate moment resistance. Okay, so now that is your ultimate moment resistance contributed by your tendon. So in general, you already get your ultimate moment that contributed by the, what we call that, by your tendon. Okay, so that will be your ultimate moment. Okay, when you have your tendon in your pre-stress peak. So one thing is the main question that you want what we call that answer is either your tendon, okay, your tendon that you provide, is it sufficient to cater for your moment? Okay, your moment means that, is it okay or not? Is it sufficient or not? All right, is it enough or not? Okay, so how to do that? So if the URS requirement are not met, so if say that if it's not sufficient, so you have to provide additional reinforcement, okay, to increase the resistance of your moment. So additional reinforcement will be like your area of steel, okay, minus with your untension. Okay, it will be like AS minus with untension is required. So in a way, you will see that your moment due to your design load must always bigger than your ultimate moment. Okay, so in a way, you have like your area total steel area will be area of steel plus with the area of your tendon. Okay, so say ultimate moment. Okay, so given, so ultimate moment is normally due to design load is given like 50 kilonewton. How you get your ultimate moment, your ultimate moment for your beam? Okay, how you get is by considering the common calculation that you do. where you have your WL square over 8, and then where your W is actually your, 1.35 kk plus 1.5 kk, like that. Okay, and then you calculate your moment, so that will be your your design moment. Okay, say that the given is 50 kilonewton meter. So that one is like the actual moment that applied on the beam. Okay, right now, before this, we know what will be the resistance provided by the tendon. Okay, so we want to check, is it applied sufficient or not to the resistance provided by the tendon? So in a way, what we do is we have 50 minus 41. Okay, why 41? Because we take the previous one, which is range 41. Okay, all right. Okay, you have 43. Okay. Okay, all right. More or less, we take that one value, okay, which is 41. So you have it like 9 kilonewton meter. Okay, so 9 kilonewton meter is the difference. So it will say that at this point, okay, where if the DS is effective depth of reinforcement bar, okay, then additional tension force required. Okay, and your FA, if you look here, all right, your FA is equal to MA over DS, okay, which is, all right, your DS or your what you call that, your DS is the position of your of effective depth position of your where you want to locate your additional reinforcement. Okay, so at this point you're not sure yet. So what you have is only the difference of your moment required, which is 9 times 10 power of 3. Okay, and estimated your AS calculation. So in general, we have this FA divided by 0.87 FUIK, which is for your reinforcement bar. Normally you have like only 500. We use 500 MPa, right, for your FYK. So your AS, okay, when you provide must always bigger than this lah. What the limitation of your area, okay, provided. So let's take a look at the example given so that you have much clearer, overview. Okay, so in this case, all right, for this example, you have design untensioned higher reinforcement, which is we use as a 500 Newton per mm square for rectangular beam. Section shown in figure below, which is stressed by 5 mm wires. So for the pre-stressing, they provide 5 mm wires, only one layer. So if the ultimate moment resistance is to exceed 40 kilonewton meter, right, for concrete strength 40 MPa. Okay, so the characteristic strength of tension still given for strength proof stress will be 1600. Okay, so if you look here, the 2HA, just first at beginning you don't see the what you call the H10, the 2H10 bar. Okay, let's say the first we assume that there is no 2H10. Okay, what is provided is only the 5 mm wires. 5 mm wires. Okay, that's only provided. Okay, because we want to check if there's sufficient for a moment or not. Okay, so what we do, okay, so what we do is we have like a strand, the strain B, SB, okay, and here they draw for the upper reinforcement as well. Okay, and then the same thing, still you have the concrete maximum strain will be 0.0035 considered here, and okay, and then the stress is 0.567 stress, okay, and the height is for the block is 0.8x. Okay, so here is where you consider the D. This is your D for your A, and D for your B, and then this is your D of A, the position of your reinforcement that you want to provide. So what to do? So first we check what will be your ultimate moment resistance that provided by your tendon. Okay, so here is your gamma M. Okay, you have your F because you have five, what you call that, numbers. Okay, your 19.6 is calculated the area before. It's the same because it's a 5 mm diameter. Okay, and then you have your what you call your stress, for your proof stress for your tendon, divide by the what you call the parameter. Okay, and multiply with 10 power of minus 3, and then you get 123 kilonewton. Okay, that will be your maximum tensile force. Okay, and your concrete compressive, this is your, sorry, this is gamma P, not gamma M. This is gamma M. Okay. Alright, so concrete compressive area to balance. So you have 123 times 10 power of 3 divided by this. Okay, and you get 0.8 multiplied with 120x. Alright, so you equal the equations 123 times 10 power of 3 divided by 0.567 times 40. Okay, in this case, so equal to 0.8 multiplied with 120x. Okay, so in a way, whereby this is the area, okay, 0.8 at 0.8 here, and 120 is actually your B. Okay, multiply with this x lah. This is the x value that you use. Okay, so the area actually they just, you know, the compressive area to balance just to get your x. So this is just based on your, you know, you have like your what you call that, stress, which is your stress concrete. Okay, your P over the what you call that, 123 kilonewton. 123 times 10 power of 3 divided by 0.567. So this is the force. Okay, the force and divide by the 0.67 of, okay, and you have like your x. Then after this calculation, you multiply it. Okay, your x is equal to 56 mm. This one, right? So at the when you have your steel stress, your gamma P, okay, which is 0.9. Okay, after losses, you know, we consider after losses, which is the initial stress was 1,120, and then you have 30% of your K, which is you can get like 705, and by considering after losses, you can consider your strain, okay, which is equal to 0.0034. This one is very straightforward, I think. So when you calculate your total strain, you consider, because we know that the strain must be additional of the strain plus bending strain. So you plus this two values, okay. Okay, all right, and you have this. Okay, and you calculate. Of course, you put every the values, d, x minus, and so on, and with the condition of your x is equal to 56. Okay, and then you will get like the total strain is equal to 0.017. So this is more than the yield. Means the yield that, you know, provided by the what you call that, for the tendon. Okay, and the lever arm that you estimate is around 253. Okay, and the ultimate moment resistance. Okay, by considering 250 multiplied with 120, then you will get the moment resistance is around 31. Okay, for 1. Okay, so you multiply the force, multiply with the, you know, the z value, the 253. Okay, you will get would be the ultimate moment. Okay, all right. Then what you call that? And it says in your question, whereby the ultimate moment is supposed to be 40 kilonewton meter, but the one can be provided by the tendon is only 31.1 kilonewton meter. Okay, you see there's a big difference there. So in that case, you see the difference will be around 8.9 kilonewton meter. Okay, so what to do? So what to do is where you have to we know that the tendon that we provide in the beam is not sufficient to cater the ultimate moment provided by, you know, that being applied. Okay, so we need to have additional reinforcement. Okay, so to have the additional reinforcement, okay, that's why we come up with what we call that. Okay, we decided to provide somewhere here. So we provide D is equal to 245. Then question I will being asked by students, okay, how to know the position of your reinforcement to provide. Basically, you can put anywhere you like, okay, but somehow rather normally it will be slightly above the tendon, okay, and of course you have to obey, or you have to also what we call that, justify, uh, what we call, there will be, what say that, there will be like, kind of like, uh, you have to consider also the spacing allowable, okay, based on the standard. It's like when you do the checking for spacing, is it okay or not, and something like that. So when you want to decide to put, to locate your additional reinforcement, okay, so then you have to ensure that you fulfill the gap and the spacing as well, okay. And the lever arm to additional strain is around 220. You just calculate, what will be the position to the force and the additional tension force required. So how to know the additional? You just take the moment, right? And then you divide with 220, which is the lever arm, because we know that when you want to calculate your moment, is your moment is your force multiplied with your lever arm, right? So when you want to know what will be the force, so you divide back with the lever arm, then you know what is actually the force. Okay, the tension force for your what we call for your additional steel, okay, that you will place at 245. Okay, so once you know the force, so you will estimate the force required is around 40.5 kilonewton. Okay, so you divide with the strength, because you know that when you have the stress is actually P over A. So you want to know what will be the area, sufficient area, so you just P over stress. So in this case, for your stress, okay, for your stress of your steel is actually equal to 0.87 times 500. Okay, 500 is your FYK. Okay, then you will get your area is around 93 nm square. Okay, so which is sufficiently the area that you should provide, that will based on your 40.5 kilometer. So in this case, you just refer to your reinforcement table, okay, and whereby you will have like 157 nm square, okay, and you will try to 10 mm diameter, okay, which is having 157 mm square. So that's what you have here, where you provide 2 H 10, the two bars. Okay. Okay. Alright. So once you design, what are the area, how many numbers to provide, and so on. You want to check the steel strain. Is it okay or not? Is it within the allowable strain or not? Okay. So if additional steel has yielded. So what does it mean? When it's yielded means that you can use means that it's already at the maximum, which is FYK is equal to 500, okay, MPa, right? So 157 multiplied with 500, okay, divide with the gamma, okay, and you will get like your this is 457 is the area, so you get the force, which is around 68.3. So you will see, well, after yielded, you will get your total tensile force will be 191.3. So you will add with 123. Okay. So those 191.3, which is your what you call depth. You want to know what will be the depth at neutral axis at ultimate when the steel is sealed. So you will consider, you kind of like backwards the calculation, where you get the x value, which is you include the compressive values of 0.8, supposed to be 0.8x, right? So then x will be the other side, and then you get what is x. Okay, so then you will have like then you can calculate what will be your strain. for your bottom, okay, and strain for your upper, okay, because you know what will be your X. Okay, you kind of like backward calculation, like before you estimate this and then you do one by one because to know what will be the sufficient X, right? Okay, so when you get this, then you will see either it's more or less than the yield. So at this point, you get the strain SV for the bottom will be more than the yield. Okay, and for 0.0062 is also more than the yield. So this value is greater than the yield strain. All right. So so when you do the so after that you check the ultimate moment resistance. That's what you conclude. Yeah? Both will be more than the yield strain. Okay, so taking moment at the center of the compression. So by taking 123, okay, and you multiply with the D. Okay, this is all the D for what you call the position of your steel. Okay, one is from your pre-stress and one is from your additional reinforcement. Okay, and to multiply, your ultimate moment will be equal to 43.8. Okay, so it had been found that either the in B, either pre-stressing steel, okay, or untensioned steel had not yielded. Okay, then try and error approach similar to would have been necessary. If it had been found in it is not yielded, so then try and error approach similar to example 11.10 will have been necessary. So since that we see that it's yielded, means that the value is greater than the yield strain, so means that your steel is yielded at that point. So because it's more than what will be the yield, okay, so it means that it's not necessary. But if say that you found it's not yielded, means it's lesser, okay, then you have to repeat again what you have done in your previous example, okay, to get what will be your ultimate moment value. Okay, because at this point we consider is is yielded, so you can proceed with the X, which is 88. Okay, all right. I think I think that's all. I hope I make it clear. Okay, the example given. So it's a very long, I would say a very long slide because there are kind of like interaction here and there. So whatever you see in this video, if you watch it through Microsoft Teams, there will be like lots of lag, a bit lag lah. I mean, not really lag. It's just because it's a live, so I didn't edit it. So I will try and see if I can edit it in the Microsoft Stream, but I think I will see later on how if I could I will. But what I'm gonna upload in my YouTube will be the one that edited, means that I will skip those sometimes there's a sound and because unfortunately I have flu this morning, so that's why I keep like have to off my mic due to that. And yeah, I think that's all. Okay, I hope at least for us even we don't have actual class today, at least we still be able to go through the site. Okay, and if you have any further question regarding the exam this chapter or this topic, please don't hesitate to ask, and you can always ask me through WhatsApp or any medium that you are comfortable with. Right, so I think that's all from me today. Okay, thank you so much for your time watching this, and don't forget to scan the QR code for your for your participation, to record your participation with the course. Okay, so because it's very important for me to get how much you have involved in this course. Okay, with that, thank you very much. Take care, be safe. So I'll be seeing you inshallah next week in our regular session. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.